Good morning. Today we're going to start our discussion of Chapter 20, where we're going to be talking about another specific type of reaction, and these are electrochemical reactions. Or more broadly, we're going to be talking about the area of chemistry known as electrochemistry. Now, we've sort of looked at these already in some level of detail back in Chapter 5, and I'll refer back to that various times throughout the chapter, but especially in this beginning part. So if we kind of just start at the beginning, right, when we think of electrical charge, right? Electrical charge is just simply the moving of electrons, right? So, for example, lightning and batteries are two examples of where we see this movement of electrical charge, or examples of these electrochemical reactions. So if we just look at lightning as an example, because we've all seen lightning, it's a quite dramatic example. Right? So in the atmosphere, right, positive charge builds up at the top of thunderclouds. It's created by the collision of typically small ice crystals that remove electrons, or electrons get moved around. And we build up positive charge, and this rises to the top of the thundercloud, and negative charge builds up at the bottom of the cloud, creating a charge separation. This pathway, this conductive path, this separation of charges, now exists, and it can allow the flow of massive amounts of electrical charge between them, and this creates lightning. Now, the vast majority of lightning occurs in the atmosphere, in the clouds. Right? It doesn't actually ever reach the ground, and we can see this sometimes up in the sky. I mean, we call it sheet lightning or other sort of words for it. But when clouds get close to the ground, the Earth develops a positive charge, and the cloud to ground lightning occurs between the negative charges that are present at the bottom of the cloud base and positive charges on Earth. And that creates, again, a conductive pathway, and that discharge there creates what we call cloud-to-ground lightning. Now, while lightning is a very visible example, there are many other examples of this in everyday life, such as batteries, right, which have this same sort of idea. They have a separation of charge within them, and when those two positive and negative areas are connected by something that allows for electrical conduction, like a wire, then you'll see discharge, you'll see flow of electrons. And this is what we're going to be sort of exploring in this chapter. We're going to be looking at chemical reactions that allow this flow of electrons. Batteries being one place where we utilize these chemical reactions to create this flow of electrons. So specifically, again, this information was in Chapter 5.9 in your textbook. You want to definitely go back and review the basics of electrochemistry. They will not be reviewed in this chapter, and so it sort of starts assuming that we understand the basic vocabulary and how to do some of these things. So I'm going to do a brief review of a few of the more important points, and then we'll pick up where this chapter starts with balancing electrical chemical equations. So, the generation of electricity from spontaneous, what are called redox reactions. So, these reactions often go by different names. They'll be called electrochemical reactions, they'll be called oxidation reduction reactions, or they'll be called redox reactions. And these are all just different names for the same reactions. And they're the reactions where electrons are transferred from one atom to another within a chemical process. Now, again, these are going to be spontaneous reactions, right? We put the right materials together and we get this spontaneous transfer of electrons. So within this reaction, there are two processes occurring, and hence where the name comes from, right? There's oxidation and reduction. Oxidation being the loss of electrons, reduction being the gain of electrons. Now, one way that we follow the electrons is to look at what we call the oxidation state. Now, remember, oxidation states are not ion charges. Oxidation states are a set of rules that we can apply that look at where electrons are likely to be based on their environment. So these are looking at whether something is likely to have more or less electrons than sort of its elemental state. So in the process of oxidation, right, where you lose electrons, it causes that atom to develop a positive charge or an increase in oxidation state, right? The oxidation states gets more positive, right? So within a lot of these reactions, we don't actually develop charges with the transfer of that electrons because they're part of compounds, right? But we will see an increase or a more positive oxidation state when we apply the rules. Reduction, the gain of electrons, is also looked at as the decrease in oxidation state, and that's actually where the name reduction comes from, right? The reduction in the oxidation state. And so in other words, it's getting less positive or potentially more negative, right? With the gain of electrons. And so we're going to utilize oxidation states as a way to follow these reactions. Now, as I mentioned before, these are assigned by a set of rules that were also covered back in Chapter 5. And I'm going to go review sort of the basics of these rules in the next slide. But remember, these are not ion charges, right? These are not real measurable charges. These are just a way to look at whether something has more or less electrons than its neutral state based on the environment that it's existing. So assigning oxidation states follows a simple set of rules. So first of all, anything in a chemical reaction that is in its elemental state, so whether it's a metal or an elemental gas like H2 or O2, right, it's given an oxidation state of 0 in its elemental form. If you're seeing a chemical reaction and they write it out using atomic ions, so they just show you, say, sodium plus ions or whatever, then it's assigned an oxidation state equal to its actual charge. Now, within compounds, we can have some rules for assigning oxidation states as well. So metals within compounds, if it is a group 1 metal, then we assign it a positive 1 charge or oxidation state. If it's a group 2 metal, we assign it a positive 2 oxidation state. Now, you'll start to see themes here that a lot of these oxidation states are the same as the common charges that these elements would take on if they were to form an ionic compound. Now, nonmetals in compounds are assigned according to a priority system. So, based on this table, you can see the priority system here. So, fluorine has the highest priority and is given a -1 oxidation state. Now, hydrogen is given a +1 oxidation in compounds and typically doesn't have anything to compete against, since the only other thing that's going to want a positive oxidation state are going to be metals. So, other nonmetals are going to be sort of competing for the negative oxidation state, and that's why we need the priority. So, oxygen has the second highest priority under fluorine, and it would have a -2. Any halogens besides fluorine, like chlorine, bromine, right, they would be next with a -1. Other atoms within the group 6, so below oxygen, so like sulfur, would also be given a -2, but have lower priority. And then finally, group 5 atoms, like nitrogen, those are going to be given a -3, but again, have the lowest priority. So for example, if you had both nitrogen and oxygen in a compound, right? Oxygen is preferentially going to get the negative oxidation state, and the nitrogen will have to take on whatever oxidation state fits. Now, how do we know what oxidation state fits? Well, that brings up the last rule, which is, or anything that we don't have a rule for, or if we have competing rules, the oxidation states of all the atoms within the compound have to sum up to the charge on the compound. So if this is a neutral compound like water or carbon dioxide, then all the oxidation states would have to add up to 0. If it was a polyatomic ion, then all the oxidation states would have to add up to the charge on that polyatomic ion. So we can see why, if there we have an example like NO2, and oxygen gets the -2 charge, right? And so we have 2 oxygens, each with a -2 oxidation state. So the nitrogen, while it can't take on a -3, it has to take on an oxidation state that is going to make the total 0. So that means the nitrogen would have to take on a +4 oxidation state. So we have a +4 oxidation of nitrogen, a total of -4 from the oxygens. It adds up to 0, which is the charge on this neutral compound. So that's the idea. Now, again, redox reactions involve oxidation and reduction. These two processes must occur together, simultaneously, right? If something is losing electrons, something else must gain those electrons. And so they have to occur together and simultaneously. Now, 2 other vocabulary words that we want to make sure that we review are the so-called agents that we have. So the reactants within a redox reaction, one of them is going to be what's called the reducing agent, and that is the agent that causes reduction. So the reducing agent causes reduction. So that means it itself would contain the element being oxidized. So by being oxidized, the reducing agent causes something else to be reduced. So some element within the reducing agent is what undergoes the oxidation. Now, of course, the oxidizing agent is just the opposite, right? This is the reactant that causes the oxidation in another one. And so that means the oxidizing agent must contain the element that undergoes reduction. So by being reduced, the oxidizing agent causes something else to be oxidized. And so these work with each other, right? The reducing agent causes reduction in the oxidizing agent. The oxidizing agent causes oxidation in the reducing agent. And so we have oxidation and reduction are the processes. Reducing agent and oxidizing agents are the actual reactants that are involved. So the next thing that we're going to talk about is what we call the method of half reactions, which we brought up a little bit in Chapter 5, but we really will start to utilize now in Chapter 20. So when we deal with a reduction, oxidation reduction reaction, or a redox reaction, we like to split it into 2 half reactions to make it easier to analyze. So we split it into the oxidation half reaction and the reduction half reaction. So if we were to look at a sample reaction, we would first, before we can do any analysis, we have to assign all the oxidation states. So using the rules, we assign the oxidation states as follows. So we have chlorine, a 0 because it's element, I- being a monatomic ion is a -1. Within water, the oxygen takes on a -2, the hydrogen +1. The Cl-, right, again, another ion, takes on its charge. Within IO3-, right, this is a polyatomic ion. So where oxygen has the priority, so it's going to get the negative. So since we have 3 of them, that's a -2, -2, and -6. So that means the iodine has to be +5 because remember, we have to add up to the charge, so we have to add up to -1. Then of course, hydrogen being a monatomic ion, it gets an oxidation state equal to its charge. So what we look for now are changes, right? What's being oxidized, what's being reduced. So the oxidation reaction here involves the iodine, right? Iodine goes from -1 to +5, right? That's clearly indicating the loss of electrons, right? It's getting more positive. So iodine is undergoing the oxidation. So my oxidation half reaction involves going from I- to IO3-. Now, we see the +6 electrons. Well, we look at the magnitude of change, right? We go from -1 to +5. That's an overall change of 6 more units negative, right? And so that's where we have the +6 electrons. So we're showing the loss of 6 electrons in this oxidation process. Now the reduction half reaction, right, takes the Cl2, right, because chlorine is undergoing the other change, right? It's going from 0 to -1, or an addition of 1 electron. And so we have Cl2 plus 2 electrons go to 2Cl-, right? That is our balanced reduction half reaction. Again, the electrons are shown on the reactant side because they're being gained, right? We have reduction, and so we have oxidation and reduction half reactions. Now notice, in this particular one, there are other things in the reaction which don't undergo changes, right? Hydrogen and oxygen, right? When we go to the formal balancing process, we'll see how all this comes to play, right? Where these other species might come from in our reaction. So this chapter really formally begins with talking about the balancing of these redox reactions in section 2 of the chapter. And so we're going to take all this basic information that we mostly learned in chapter 5, and now we're going to start to apply it. So the balancing reactions, we're going to use what's called the half reaction method, right? So we just talked about these half reactions, so we're going to start with these half reactions to allow us to come up with the balanced redox equation. And so the reaction is first broken down again into the 2 half reactions, the oxidation and the reduction, and then we balance them individually for both mass and charge, and then we add them back together to get the overall balanced equation in solution, right? So all of these reactions are going to mostly be involving aqueous materials, right? Things we're going to be working in solution. So let's go over the basic formula or the basic process we're going to use for balancing. So the first step is we have to look at our reaction and assign oxidation states to all of the elements in the reaction. So we have to go through and figure out what are the oxidation states, and so that we understand what's being oxidized and what's being reduced. Then we can write the half reactions. So we can break it down into our 2 half reactions. Then we can start the balancing process for each half reaction. So first, we balance elements other than hydrogen and oxygen. So we balance non-hydrogen oxygen elements. Now here we're balancing by mass. So this is just like we've balanced equations before. So we make sure we have the same number of each type of element on both sides of the equation. Once we've balanced other elements, we then balance the oxygen by adding water, right? So the key is the way that we're going to balance the oxygen, right, is to add water to the side with fewer oxygens, right? So if we need to add oxygen to balance with the other side, we're going to add the number of waters equivalent to the number of oxygens we need. Now, of course, by doing this, we're adding extra hydrogen as well. So then we're going to balance the hydrogen by adding H+ to the side that needs additional hydrogen. So we're going to balance oxygen by adding water, then we're going to balance hydrogen by adding H+. Now, this balances in what we call acidic solution, right? Notice the H+ ions. But if we are asked to balance in basic solution, which sometimes we will be, then we are simply going to add hydroxide ions to both sides in order to neutralize the H+. So on whatever side the H+ is on, we're going to make water, and then on the other side, we're going to end up with excess hydroxide ions, or in other words, we'll be in basic solution, right, with those hydroxide ions. Once we've balanced by mass, we're going to balance by charge by adding electrons, right? So we know that the oxidation is going to show electrons on the reactant side, or excuse me, on the product side. The reduction half reaction is going to have electrons on the reactant side. So we want to make sure that we have the right number of electrons to balance the half reactions. At that point, we need to make sure both half reactions have the same number of electrons being lost or gained, right? We can't lose 2 electrons and gain 1, right? We have to manipulate the half reaction so that we show the same number of electrons being lost and gained. Once we have charge balance to go with our mass balance, we are then going to add the 2 half reactions back together and check it to see that we have an overall balanced equation by both mass and charge. Okay, so that's the basic process. Let's do an example here real quick. So our starting reaction is going to be here. So we have iron 2 plus MnO4 minus permanganate ion goes to iron 3 plus manganese 2 plus ions. Right? So this is what we're given. So our first goal would be to assign the oxidation states. Right? So you can see them listed here. We've used our rules to assign our oxidation states. We figured out that the iron is being oxidized and the manganese is being reduced. Okay. So the second part is to write out our half reactions. So we have our oxidation half reaction, right? That's here. And we have our reduction half reaction, that's here, right? So we have iron 2 plus going to iron 3 plus. The manganese is in part of permanganate, MnO4 minus, goes to manganese 2 plus. So we have our oxidation reduction half reactions. Then we balance by mass. So the first one's pretty easy, right? Our oxidation half reaction doesn't need to do anything, right? There's 1 iron on each side. There's no oxygens or hydrogens, so we don't have to do anything. So pretty much that one's done. Now, on the other hand, for the reduction half reaction, right, the manganese is balanced, but we have 4 oxygens on the reactant side. So that means we're going to add 4 waters to the product side to balance the oxygen. Well, of course, that means we added 8 hydrogens here. So we're going to add 8 H pluses to the reactant side to mass balance our equation. So we've mass balanced. Now we're going to charge balance. So if we look at, we're going from iron 2 plus to 3 plus. That reflects a loss of 1 electron, right? So we add 1 electron to the product side to balance our charges. Notice that on the reactant side, we have an overall 2 positive charge. On the product side, we have 3 positive and 1 negative. You add that together, you get a 2 positive, so you have a 2 positive charge on both sides, right? That's what we mean by charge balance. For the reduction half reaction, right, if we look at the charge, and when we're up here, right, we have a positive 8 and a negative 1. So we have a positive 7 over here. Over here we have a positive 2. So that's going to reflect a 5 electron reduction, right? We've gone from positive 2 to positive 7, right? That's, or positive 7 to positive 2. That's reflecting a 5 electron gain in oxidation state. So we're going to show a gain of 5 electrons, and that will balance my charge on both sides. So if we look at this, we have 5 negatives here, 1 negative here, so that's 6 negatives, 8 positives, so we have an overall 2 positive charge on this side, and an overall 2 positive charge on the product side. So now we've balanced both half reactions by charge. So now we have to make sure that we have the same number of electrons being lost and gained. So here we clearly have only 1 electron being lost, but 5 electrons being gained. So we have to equalize that. So the easiest way to do that, to make both of these the same, is to both make them equal 5. So to do that, we simply have to multiply this equation by 5, and we end up here with 5 iron 2 plus going to 5 iron 3 plus 5 electrons. Now, if we look at these two, we have a 5 electron loss balanced by a 5 electron gain here. So now we're going to take our two balanced equations, balanced half reactions, and put them back together. Right? So we're going to add up our two equations. So here are our two final half reactions. We're going to add these together. Notice the electrons will cancel, right? Because we show 5 electrons being on the reactant side, 5 electrons on the product side, so those cancel. So on the reactant side, we have 5 iron 2 plus, we have 8 H plus, and we have 1 permanganate. On the product side, we have 5 iron 3 plus, we have manganese 2 plus, and we have 4 waters. And this gives me my balanced equation. Now we double check it. First mass balance, we have 5 irons on each side, we have 8 hydrogens on each side, 1 manganese, and 4 oxygens on each side. Charge, if we look at the overall reactant side, we have 10 positive here, 8 positive here, so 18 positive, and negative 1. So we have an overall plus 17 charge on this side. If we look over here, we have positive 15, positive 2, and 0. So that's, again, a positive 17. So we have charge balance, right? So we have a mass and a charge balanced reaction now. So this is our overall balanced redox equation. So that's the process we're going to go through to balance our redox equations. Okay, next I want to talk about two basic terms that we will use when we talk about electricity. So typically when we refer to electron flow, we talk about its current and its voltage or potential. And so just to review what those are, so electrical current is a measure of the flow of electrons, right? So if we think about current in a river, right, we think about the flow of water, and we have this idea that, you know, if we have a fast current, that means more flow. So a high current means more flow. So the same thing in electrical. So electrical current is the flow of electrons through some conductive material like a wire. And there is going to be a flow because of a difference in potential between those two ends, right? So just like water flows downhill because of a difference in gravitational potential energy, electrical current flows because of a difference in electrical potential. So the current is measured as the amount of electric charge that passes a point in a given period of time. So essentially how many electrons per second, if you will, passes by a given point, right? That's a measure of how fast it's flowing, right? The faster the current is, the more electrons that will pass in that period of time. Doesn't matter whether they're flowing through a wire, through a sheet, through a solution, right? That's what we're looking at when we think about current. Now, again, it's the number of electrons that flow per second typically. The basic unit is the ampere or amp, abbreviated by the capital A. And so 1 amp of current is 1 coulomb of charge. So coulomb, remember, is a unit of charge per second. So 1 amp current means that you have 1 coulomb of charge flowing past that point every second. Now, if we convert that into maybe a little different unit, that 1 coulomb, right, reflects 6.242 times 10 to the 18 electrons per second. So 1 coulomb, right, is 6.42 times 10 to the 18 electrons. Now, voltage, right, so we have current, we have voltage. Voltage is the potential difference, right? So this is that difference that is causing or resulting in the flow of current, right, of flow of electrons. So the units of potential difference are the volt, right? And it's a measure of the potential energy difference between the reactants and the products, right? Now, 1 volt of potential, right, is 1 joule, right? This is an energy, 1 joule per coulomb of charge, right? So if we have a 1 volt potential difference, that means we have 1 joule per coulomb of charge in the potential difference. So it's an energy, right? It's a potential energy difference. And this reflects how much voltage you would need to in order to drive the electrons through an external current or circuit, excuse me. So this is how much voltage you would need to push, right? Need to apply in order to push those electrons through some external circuit using this reaction. So, and the amount of force that we're using is often called the EMF, or the electromotive force is another term that we see for this voltage or potential difference. So now let's start to look at these reactions, right? So we're going to start with just a very simple redox reaction. So if I put a piece of zinc metal into a solution that contains copper ions, right, what we see is a spontaneous oxidation reduction or spontaneous redox reaction where zinc gets oxidized or loses electrons to form zinc ions, and copper ions take on those electrons to form copper metal. So the copper ions get reduced. So this is one example of a spontaneous redox reaction. So I put that zinc in there, and the copper ions will spontaneously start to accept those electrons to form copper metal at the surface here. And at the same time, the zinc is essentially dissolving, right? The zinc is being converted into zinc ions, which go into solution. And those electrons that are generated are accepted by the copper ions and form copper metal. Now, this is great. We can observe this reaction, but it's not terribly useful, right? Because we can see the electrons are just flowing over a very small pathway. Right? You know, if you look here, the atoms and ions are essentially in contact, right? The zinc atoms on here, when a copper ion gets close enough to the zinc, right, the zinc will transfer its electrons and leave as a zinc ion, resulting in a piece of copper metal sitting on the surface here. But we can't take advantage of these electrons, right? They just jump from one species to the next, and so there's really no advantage here. We see it, but how do we utilize this flow of electrons from the zinc to the copper ions? Well, we set up what are called electrochemical cells, or a voltaic cell is the most common, sometimes called a galvanic cell, but these are cells made up of spontaneous redox reactions. So the difference in potential energy between what is called the anode and the cathode, and we'll define those terms a little later, in a voltaic cell is called what we call the cell potential. So this is going to be the potential difference between the reactants and the products in our balanced redox reaction. So this is called the cell potential. So voltaic cells, right, generate electricity via the occurrence of spontaneous redox reactions. Now, depending on what species you choose, right, you'll get different cell potentials because it depends on how easily one of your reactants loses electron and how easily the other one gains the electrons. So it's the relative ease at which your oxidizing agent, right, is reduced or gains electrons at the cathode, and how easily the reducing agent, right, loses electrons at the anode. Right? So it depends on the species involved how big this potential is going to be. Now, we measure these under what are called standard conditions, right? And this should be familiar to us now, right? That what we mean by standard conditions is 1 atmosphere for gases, 1 molar concentration for solutions. And typically, for these kind of experiments, we're also thinking about standard temperature or 25 degrees Celsius. Now, this is called the standard EMF or the standard cell potential. Right? So we have our cell potential, and under standard conditions, so just like we saw in thermodynamics, we use the little degree sign here to indicate that this is the cell potential under standard conditions. Now, we can generate this value by looking at the cell potentials of the 2 half reactions involved, and we simply add those together. Okay? And that's going to give me the overall cell potential for the reaction. So in order to make this useful, we're going to separate the 2 half reactions, right? So instead of having the zinc in the same solution as the copper, so essentially oxidation and reduction are taking place right next to each other, we're going to separate them physically, and so that we have to then provide a pathway for the electrons to flow from the site of oxidation to the site of reductions. But of course, in that process, we can potentially utilize those electrons to do something, to do work. Okay? So we're going to allow the electrons to flow through a pathway like wire, and we're going to see ion flow through a solution, and so this circular flow of charge will create an electric circuit, right, within our voltaic cell. Now, we have to have conductive surfaces to allow these electrons to flow, right? So they're not going to jump out of solution. So we have to provide typically a solid electrode that will allow those electrons to move from one side to the other through some sort of external circuit. So these electrons are typically made of some sort of metal, right? Often the metal that we're looking at, or they could be graphite. We also have to have a pathway for ion exchange. right? So not only do we have to have a pathway for electrons to flow, we have to have a pathway for ions to flow between the two half cells. This is called an electrolyte, right? We need some electrolyte connecting the two solutions to allow ion flow, right? This helps maintain charge balance in our solutions, right? And we'll talk more about this as we go through about why that might be important. So a little bit more vocabulary. So within this voltaic cell, we have two electrodes. We have the anode, right? This is the electrode of oxidation, right? So the anode is the electrode where oxidation occurs, right? And that's always to go together. So oxidation, anode, you might want to remember the two vowels go together. Oxidation at the anode. And this is going to be assigned the negative charge in our voltaic cell, right? It's the negative electrode. The cathode, right? This is the electrode where reduction takes place. Now, one way to remember this, again, is the two consonants stick together, right? So we have R and C. So reduction always at the cathode, oxidation always at the anode. Two vowels together, two consonants together. The cathode is assigned the positive sign in terms of the electrode sign. So we're going to have electrons flowing from the side of oxidation, or the negative side, to the side of reduction, to the positive side. So we always flow from anode to cathode, from oxidation to reduction, from negative to positive. That's how the electrons flow. Now, the most standard way to do this is simply to allow the anode to be made of the same metal that is being oxidized. Right? So in our example that we had, right, zinc was being oxidized, so in the oxidation half we would probably use a zinc electrode, for example. And the cathode is typically made of the same metal that is being reduced, or that is being formed by the reduction, if it is a metal that's being formed. And so in our example, we might use a cathode of copper, since we were generating copper from the copper ions in solution. Now, if the redox reaction involves the oxidation reduction of an ion, right? So not the metal, so we can't really just use the same metal, or a gas, then we have to use maybe different electrodes. So we might use some sort of inert solid that is not going to get involved. Right? So an inert electron is one that allows the electrons to flow but doesn't actually participate. So examples of this, common examples of this, are platinum metal or graphite are often used as inert electrodes if we don't have a convenient solid electrode that we can use that sort of matches what's going on. Now, I said there must be a pathway for ion exchange between the two reactions, and that's what's referred to as the salt bridge. And so this is some device, sometimes just a U-tube of glass, or some mechanism that is electrolyte, that contains an electrolyte solution that allows ions to move between the solutions or into both solutions from this salt bridge. So if we revisit our picture here, right, so what we notice here by looking at this reaction is that clearly zinc has a greater tendency to undergo oxidation here, right? Otherwise, no reaction would happen, right? So zinc wants to lose electrons, and it wants to give those electrons to copper. So that means what that's telling me is that zinc has a greater tendency to oxidize than copper. And this creates a potential difference, right? Because it wants to go, and so since it wants to go, there's a spontaneous difference in potential, and how big that is, means that there's a bigger difference. You have a bigger desire for those electrons to flow, and it creates a bigger potential difference in your cell. And so we'll get more into this and talk more about this as we sort of go through the material. So the last thing that I want to do in this session is just to look now at our completed voltaic cell that we might put together. So I've used the same reaction that we saw before when we took that piece of zinc and put it in a solution of copper ions, and we saw the spontaneous oxidation of the zinc and the spontaneous reduction of the copper ions. So now we've taken those same processes. Okay? As you can see here, we have the oxidation of zinc and the reduction of copper ions, but we physically separated them into two containers, right? Two half cells. And so we have the oxidation cell here that has our anode being made out of the metal that is being oxidized, the zinc. Now, we have to have a solution here. So for convenience sake, we often make the electrolyte solution here just simply contain the same metals, the same ions that are going to be produced. So since these are going to be oxidized from zinc to zinc 2+, we often will just use an electrolyte solution of zinc 2+ ions. So like, for example, a zinc nitrate solution. Nitrates are very common because nitrate ions don't tend to get involved in electrochemistry. So for example, we would be unlikely to use, say, chloride ions or zinc chloride, because chloride ions can undergo oxidation reduction processes. It can start to get involved in some of these to create unwanted reactions. So we use a lot of nitrate ions here because the nitrate is pretty stable under electrochemical conditions here. Now, we have now a pathway, right? So on the oxidation half, we have oxidation occurring. So we connect all this together and we have oxidation occurring. So we create zinc ions here. The electrons that are created will flow through the available pathway. Right? So they're going to flow up here and through this. So while these are moving, we could choose to have it do work like light a light bulb or move a fan, something like that. And they're going to flow. Now they're flowing, right, because of this potential difference, right? This downhill, right? This current, right? There's a potential difference that's causing, by connecting it to the right ion to be reduced, right? We create a potential difference which creates the spontaneous flow of electrons to the cathode side, where the reduction side of the cell. So the electrons flow. Once they get into solution, they will be gained by, in this case, the copper ions that are in solution here. Those copper ions will take on the electrons to form copper metal, and we'll see a buildup of copper metal along here on our cathode. Now again, for convenience, our cathode is simply made out of the metal that we're creating here. In that case, copper. So we're going to plate out more copper metal on top of our copper electrode. Now, so we've provided a pathway for electron flow, but that's not enough, right? We have to have a circuit, right? We have to allow the charge to sort of continually move. Now, the electrons are not going to flow through here, but ions will move, right? And they'll move in such a way to replenish what's going on. So on the oxidation side, right, we're creating positive charge. Now, we need negative charge to balance that out. And so the source of that, right, is our salt bridge, right? So we have a flow of negative ions. Now, why might we think about that? Well, as negative charge flows away, negative charge flows into here in the form of these nitrate ions to replace it, right? So we're seeing the negative flow of negative charge here and through here. And once we get here, right, that negative charge is going to combine with the positive charge here and deplete it. So we're going to have a depletion of positive charge here. So we need to replace that positive charge to complete the process. And so we get positive ions flowing out of our salt bridge to replace the positive ions that are being depleted as part of our reduction. And so in this case, our salt bridge is an electrolyte of potassium nitrate. Typically we try to use a very sort of simple salt here, like potassium nitrate, could be sodium nitrate, right? Nitrates, again, are very common, along with group, sodium, potassium salts, are very common in these, where our potassium ions and our nitrate ions are going to act to negative charges. Negative ions will always flow toward the anode to replace the electrons. Positive ions will always flow toward the cathode to replace the positive ions that are undergoing the reduction. So in this case, we've completed a circuit. So we have the same process going on that took place in that one beaker, but we've pulled it apart so that we can take advantage of the flow of electrons, the current here, to do something, to do work. And this is the basis of what we call a voltaic cell. Now, later on in the chapter, we'll look at batteries, and batteries are simply a voltaic cell, but one that's been nicely packaged in an easy-to-use, packaging. Now, it can get a little cumbersome to draw out an entire voltaic cell sometimes. So, a lot of times, once people get used to this, instead of actually drawing out the whole picture, we use what's called standard cell notation. So this is a shorthand representation of an electrochemical cell. And so by drawing this, you're telling somebody, okay, this is the voltaic cell that I'm using, right? And so we have some standard conventions. Now you notice in the picture that electrons always flowed left to right. So they always flow from the oxidation side on the left to the reduction side on the right. And that's how we'll write out our cell notation. We'll go from oxidation to reduction. Now, we'll separate the two sides by two vertical lines. Now, if we have a phase change, they're going to be separated by a single vertical line. So this might be a separation between a solid electrode and a solution. Or, this would be what we mean by a phase separation. That'll be a single line. So it's a phase change. If we have multiple species in the same phase, like in our solution, we just simply draw them both all out using commas to separate them, right? We don't use lines because they're part of the same phase, right? They're in the same solution. The double line, like that I referred to up here, right? This is the salt bridge essentially, right? So we're separating our oxidation and our reduction half with this double line that's indicating the salt bridge. So the way we would draw it out would be our anode is a phase change to our electrolyte at the anode side. The double line represents the salt bridge. On the other side of the salt bridge is the electrolyte on the cathode side, and then finally the cathode electrode. So if we apply this notation to the cell that we just did, the way that we would write it out would be the following, right? We would have our anode of zinc, a single line, and our phase of zinc 2+ ions. Notice I don't necessarily need to draw out the spectator ions, in this case nitrate ions, only the ions that are involved. So zinc 2+, aqueous, we have our salt bridge. On the other side we have copper 2+ ions in solution, and then our cathode made of copper. So by drawing this out, somebody else could look at this and recreate this cell, or say, oh, okay, I see they have an anode, an oxidation side of zinc metal and zinc ions, and a cathode side of copper ions and copper metal. So that concludes today's class. Next time, in the next section, we will start looking at what are called standard electrode potentials. And this is how we're going to be able to get a measure of these cell potentials that we want to calculate.